Hi everyone, thanks for joining our session. Today I'll be presenting on BloomNet, Blockwise optimization for masking networks towards scalable and efficient speech enhancement. My name is Sunwoo Kim, and I advise under Professor Minje Kim at Indiana University. This material is based upon work supported by the National Science Foundation. So scalability is an important feature for many multimedia applications. Let's take as an example scalable video coding. I'm sure everyone's had this scenario where you're watching a movie through a streaming service and you have a good internet connection, so you experience it at 4K quality. Then, unfortunately, the connection drops and you may need to wait. If it were not for the scalable video coding, a scalable video codec tries to avoid this buffering by adjusting to the target user's internet connection and reduces the bit rate so that the video can keep playing, but just with a reduced video quality. And users are generally happy because most people rather watch it at lower quality than to wait for buffering. And you can think of this as a similar concept to the operating modes of, say, a Dyson vacuum. It has this auto mode where the vacuum can automatically adjust to optimize its cleaning power as you move on to different surfaces, so that it can give you a good balance of power and runtime. Now, in the context of source separation or speech enhancement, let's suppose you're talking on the phone and your device is doing some active speech enhancement using complex machine learning models, trying to improve the speech quality. And say you're also doing a video chat. So this combination of using the screen, camera, speakers, and the mic all in one device works the phone really hard and drains the battery pretty quickly. So it'll be ideal if the machine learning based speech in a system is scalable, so it can go into some sort of battery efficient mode, so that users can still hear somewhat enhanced speech and not have to worry about other applications and the battery. So in our scalable speech enhanced system, we want to adapt to the varying limitations of the resource, such as power, which would correspond to the internet speed in the video coding example. And one example, like one approach to a scalable speech enhanced system would be to have several different versions of the enhancement model, like preparing a low complexity model, small model for its energy efficient mode. There's a medium sized one, and a large one. So this way the system can pick one depending on how much it wants to be conservative on the resource. Say if we have enough resources and the phone isn't doing much, then the system can pick just the big module and get the best performance. And if we're low on battery, then we can pick the smallest module. So this design offers scalability, although it's not effective in terms of memory usage though, since it has to hold all three versions. If the number of parameters for the small, medium, and large models were 1 million, 2 million, and 3 million respectively, then we'll have to store 6 million in total. So we propose BloomNet, the name dedicated to our hometown, Bloomington, Indiana. We propose BloomNet to convert a popular time domain masking-based source separation models, such as CompTestNet or dual-path RNN, into a scalable version. We train each of the blocks in its separation module sequentially in a greedy manner so that the model can do blockwise processing and optionally choose to use only the first few blocks depending on the available compute resources. For example, if we have plenty of computational resource, we could use all the blocks, all L blocks. Or if we're running low on battery, then we can switch to an energy efficient version and use less and just use one of the blocks. So in this setup, imagine if each block is assumed to be as small as the wee little enhancement model from before, where one block contained 1 million parameters, then the total size for the model with 3 blocks would be 3 million parameters as opposed to 6 of the naive scalable system. To build up more motivation and intuition to BloomNet, first we'll introduce some baseline models. This first baseline, it adopts a common structure found in time domain source separation networks. It consists of an encoder that takes a time domain input and maps it into a latent representation. It's usually a small neural network module. Then this latent representation is fed into a separator module, which performs residual learning with repeating blocks, where each block's output is relayed to the next as a sum of the output and its previous input. And then the output from the last block is used as input to the mask estimation module. And then its computed mask is applied to the encoded mixture representation to retrieve the source-specific estimate, such as for the speech source, which the decoder then transforms back to a time domain estimate of the target source. So all these modules are learned together. So if we try to remove any one of these blocks or modules, it would completely break down the model. To illustrate, if we used total L equals 6 blocks, we're able to reach up to 9 decibels SISU improvement in our setup. But when we try to use just one block, so we discard the rest, just use the first block, the model actually worsens the sample. And this is because the model hasn't seen the case of involving only one separator block during training. And when we include one more block to use the first two, there's again no improvement. And when we use more, the model still performs poorly. And this is because the modules are trained all together end to end. These intermediate outputs are not suited for the masker module, which can only work with the final L separator blocks output. So if we wanted to scale this model to different applications, we would need to train multiple versions. We would need to train all 6 different versions in this setup, specializing for each intermediate configuration. And we'll denote this as the intermediate version. So with this setup, we can get a good performance for each modes for 6 different blocks. But this is the naive solution we mentioned earlier, where we would need to store 6 different models. And the total spatial complexity is a sum of all the different models. You can see the total spatial complexity gets much larger as the number of blocks increases. So this is not the most efficient option. Although note that their enhanced performances are the best, we'll be using this, referring this as the upper bound of our proposed BloomNet framework. So to build up to our proposed BloomNet design, we have a scalable baseline that uses weak separator blocks, consisting of just one separator block in its module. So it's a compromised version of baseline 1, but still a legitimate separation model. As opposed to baseline 1, we assume there are L such separation blocks. Each are trained sequentially to enhance its previous block's results. So during test time, suppose the device can afford up to 2. Then we can just perform inference on the first block or the first 2, and we can still get a legitimate source estimate. But the disadvantage of this setup is that these weak blocks are capable of learning only shallow latent representations from its separator module. So there is a limit in performance improvements to using additional blocks. You can see that baseline 2 clearly underperforms compared to the previous inefficient but very well performing baseline. But the motivation to include this setup is that it is scalable. We only need to deploy one such model and then we can choose how many blocks we want to use flexibly during test time. But again, the performance is very limited. So finally, we get to our proposed BloomNet model that is scalable and also performs well at every scaled version. We start training with a similar setup from baseline 2, where we have just one separator block. And after it's done training, the blocks involved here are no longer updated. Then we add a second row of blocks that takes as input the sum of the input and output of the previous block, as done in CompTestNet or first baseline. Except the difference is we also add a separate masker and decoder for the second stage. And the newly added modules are trained using a block-specific loss. So this design ensures that the intermediate outputs are usable. Do note that the encoder is shared and reused for all sequence of blocks, such that all of them learn to estimate denoising mask on the same latent representation. So, and once the modules are trained, they're also no longer updated. And we add on more blocks the same way we did for the second one. And during test time, we can just choose freely the number of separator blocks. For example, let's say 2. Then we can run inference on the encoder, the 2 separator blocks, and then the masker, and then the decoder for that second block. So to clarify a little bit more, the difference between BloomNet and baseline 2 can be better explained using a stacked autoencoder as an analogy. So stacked autoencoders use a greedy layer-wise unsupervised training strategy that trains each hidden layer one at a time sequentially, And the idea is to provide the upper layers with better representations of high-level abstractions. Say it's the training starts with a shallow autoencoder with just one hidden layer. The decoder is discarded after training, and then the latent representations are then used as the inputs for the next autoencoder. So this next autoencoder is just stacked on top and trained to reconstruct the latent features here, the X2, instead of the original input X1. And the encoder from the previous layers are not updated. And then its decoder is then discarded, and so forth. So this greedy training strategy ensures that the lower layers extract low-level features and learn simpler concepts such that the upper layers can build on top of them to learn more high-level abstract features. And our BloomNet can be viewed in a similar light as this stacked autoencoder. Because after training the first block, you see it's frozen. And when you train the next block, the output from the previous one can be seen as the learned low-level features that are provided to the next one. So by adding more blocks, we're able to further extract better representations such that the latter blocks can learn higher level abstractions. And I know it's not a direct comparison since BloomNet has these residual connections, but both models use the same greedy learning strategy. And for baseline 2, using the same autoencoder analogy, it can be seen as a naive stacking of autoencoders where the first autoencoder is trained the same way. And instead of discarding the decoder, the reconstructed output is fed to the next autoencoder, and so forth. So since these intermediate representations are decoded back to the input domain, this version is only able to learn a shallow representation at each hidden layer. And this illustrates why baseline 2 showed very little improvements with additional blocks. So since BloomNet passes on better representations to the next layer to learn from, it's able to get a much better performance compared to baseline 2. And I know it's not as good compared to this baseline 1's performance upper bound, where its intermediate versions are exhaustively trained separately. So all these versions, individual versions perform optimally. Yeah, so BloomNet is trained sequentially in a greedy blockwise way. All the previous blocks are not updated after training. So this makes it scalable, but yes, it underperforms compared to the baseline 1's optimal performances. So to address this, we can do fine tuning all the modules using the sum of all the blockwise functions, loss functions. And this was also done in the stacked autoencoder work mentioned in the previous slide. So after fine tuning, you can see that this line at BloomNet is almost comparable to the performance upper bound. And since it is scalable, it's much more efficient and compact in terms of spatial complexity, since we only need to store one model instead of baseline 1, which would need to prepare and store all 6. You can see the number of parameters for BloomNet is also a bit lower than baseline 2. It's because baseline 2 needs to run all 4 modules to encode and then decode back to the time domain, while BloomNet actually shares just one encoder. So this would also make it computationally more efficient. And here are 2 denoising examples. Left to right reads a noisy mixture, the source estimates using 2 and then 4 and then 6 blocks, and then the ground truth signal for reference. So from this figure, we can see the system works as expected. If we choose only a couple blocks, say 2, the enhancement performance is good, although it could be better, but it's compact and cheaper to run. And when we use more blocks, say 4, the performance improves, and it can reach the best performance when you use all 6. So we can see the improvement is largest though for the first 2 block setting. And this is because the sequential training puts the blocks in the order of significance or the amount of heavy lifting it should be doing. That's why by the 6th block, we see the improvement is minimal compared to the previous block's results. And similarly for the second example. To summarize, we proposed BloomNet, a scalable masking-based speech enhancement model that is compact and gives good performance for any number of desired blocks. Thank you for listening. Please check out our paper for more details and feel free to ask any follow-up questions at our session. Thank you.